In this video, we will discuss tests for series with non-negative terms. Of course, these tests will tell us whether a series is convergent or divergent, but of course not what the limit value is. Okay. Now, because when we take the limit, n approaches infinity, we don't care about what the first few terms do. And therefore, we will have the following definition, or rather agreement. Okay, we say, okay, a series, okay, or a sequence is ultimately non-negative if there exists an n0 such that for every n after that, an is non-negative. Now, it is obvious that the same adjective ultimate can be used for other properties. For example, for an increasing sequence, if it's increasing after some point on, we could say, well, it's ultimately increasing, and so on. Okay, so we will be using this setup, this characterization. Now, what are the tests that we are talking about? Well, the first test that we will consider is the so-called integral test. This test, as we will remark a little bit later on, compares a given series with an improper integral. So this integral is actually an improper one. So let f be a function defined on 1 infinity into r, so it's a real valued function, be continuous, okay, decreasing, and positive, ultimately, that is, for x greater than or equal to n1 for some n. Well, f is defined starting with 1, but it will be continuous, decreasing, and positive after some point on. That is ultimately. Now, then we have the following conclusion. Then the series where an is actually f of n, and the improper integral, because it's continuous after n1, let me put n1 here, to infinity, f of x dx, are both, or rather are convergent or divergent simultaneously. That means they are both convergent or both divergent. The proof of this theorem, actually it's a theorem, shows us an insight into what we really mean. So let us go over the proof, and we will see that we will be using some previous ideas from the previous theorems. Okay, let us first of all draw a picture to understand what's happening. Now the function f is a decreasing continuous function with limit 0 when x goes to infinity. So suppose this is our n1 point, and after that n1 point, our function decreases. This is our f of x. Okay. Now, suppose we have an n bigger than n1 and some n plus 1. Of course, at this point, the value is f of n, but we called it an. And at this point, the value is f of n plus 1. We called it a n plus 1. Now, the idea is to compare the areas that we see between n and n plus 1. So, comparing areas, okay, we get, well, the area of the lower rectangle is certainly 1 at the base, and the height is an plus 1. That would be smaller than the area below the function curve. So, okay, because f is continuous in this interval, it has an integral, and so on and so on. On the other hand, the biggest rectangle with height f of n, that is an, and base length 1 is the largest one. Well, this is true for all n after n1. So we add them up. Adding up, of course, for n1 up to a capital N. Capital N is a fixed number. That gives us the sum of a n plus 1 from n1 up to n. That would be smaller than the summation here, that is n1 to n1 plus 1 f of x dx, plus up to n to n plus 1 f of x dx, and that would be smaller than the sum n1 to n of an. Okay. Now, let us look at this more carefully. It is actually, okay, starting from n1 to n, but because of this n plus 1, everything is shifted a little bit. So it is a n1 plus 1 as the first term, continues up to a n, but there is an extra term. Okay. But now, okay, we can write this as the sum n from n1 into capital N of an. Well, this means we are adding an extra term, the n first term, so we subtract a n1, but then we have to add a n plus 1. Now, the reason for this is to make this sum look like the other one. Okay, call this, okay, Sn. Note that it's not the Sn of the given series, the original one, but the one starting from n1. This is Sn, which is partial sum sequence for the series n1 to infinity. Now, this, of course, in this new notation, says the following. Then, okay, we have here Sn minus some term, but of course, an plus 1 is f of n plus 1, so it's a positive number. Okay. Thus, we get Sn minus an1 bounded by, combining the integrals together, we have n1 to capital N plus 1 f of x dx. It's bounded by Sn. Now we observe that each of the two terms, Sn and the integral, increase when n increases. So here, Sn is an increasing sequence, but also the integral is increasing with x. So we can regard them as two sequences. Okay. Now, why are they increasing? Well, simply because f of x is positive. And also, the same happens to Sn. This is because f of x is positive, so an is positive. An was f of x, remember. And of course, n is bigger than n1 in this sense. Now, to say that one of them is convergent, we only need to say that it's bounded. Well, at this point, suppose the integral is convergent. Okay. Well, let me give a name to it. Say it is convergent to L. Okay. Thus, we get this. This is because, again, f of x is positive. So this inequality holds because f of x is positive. You're adding more area when n goes to infinity. But this says that our Sn minus an1 is bounded by L, so Sn is bounded by an1 plus. This is true for all n after n. So Sn is bounded, okay, and also increasing, so converge. Now, this means, of course, the series starting with n1 is converged. Well, if we start the series from 1, the meaning is we're adding a constant to it. So it does not affect convergence, hence also the series starting from 1 is converged. Now, suppose the integral n1 to infinity f of x dx is divergent. Now this means, because f is positive after n1, okay, it means that the integral actually is infinite. Because you have a positive function, okay, and of course divergence means the sum is infinity. But then the limit when n goes to infinity of n1 to n plus 1 f of x dx is infinity. So the limit over n of Sn is infinity as well. Okay. Well, this says that the series from n1 to infinity an is divergent. Hence, adding a constant, this is also divergent. Well, this finishes the proof of the theorem, because if the integral is convergent, so is the series. If the integral is divergent, so is the series. Well, let us apply it to some example. Okay, actually, this test is, well, important in its own statement, but it's not that useful in practice, except in one case. We will consider that right away. Okay, let f of x be 1 over x to the p, okay, where p is a real number. We will assume it is positive, or rather greater than or equal to 0. And of course, for this to make sense, we need x to be positive. So we assume that x is in the interval 1 to infinity. Then, okay, because p is positive, the function is decreasing. Okay. X starts from 1. And clearly, when x goes to infinity, okay, except when p is 0, okay, limit, we of course said that, No, it should be decreasing enough. That's fine. Okay, so f is decreasing. It would be continuous, certainly, and it would be positive, okay, in the interval 1 to infinity. Okay. So the function satisfies the properties of the theorem, the hypotheses of the theorem, and so by the integral test, okay, the integral and the series converge or diverge together. But from the previous semester, we know when this type of integrals, improper integrals, are convergent or divergent. Well, this converges if and only if p is bigger than 1. Okay. And so we have the following conclusion. The series is convergent if and only if p is bigger than. Incidentally, these series are called p-series. They serve as a good test series, and we will be comparing other series with these series basically, and in that sense it's a very important consequence of the integral test. Now, you can try as an exercise, okay, for which p is the series, maybe we should start n from 2, 1 over n logarithm n to the power p is convergent. Now, this may strike a little bit strange, but we had this in improper integrals already. That's to say, when we look at a p-series, okay, we see that if the p-value is slightly above 0, like 1.0001, okay, the series will be convergent, but when it is 1, it becomes divergent. Of course, divergent means it's equal to infinity. Okay. We can apply this test in many other cases, but I will not go into that. There will be easier ways of showing convergence for such series alternatively. So I will pass to the second test. It's called comparison test. Okay. The comparison test compares a series with another series. So, okay, let an be smaller than bn ultimately. then if the series of Bn is convergent, then so is the series of An convergent. Note that we had such comparison theorems for improper integrals in the previous semester. Okay? And positivity was very important there. And 2, if the series of An is divergent, then so is the series of Bn divergent. Well, the proof again rests on the boundedness and monotonicity of the partial sum sequences. Okay, I will shortly talk about how we can prove them. Okay. Well, say ultimately these are true. So say for all n after sum n1, we have An less than Bn. Okay. And then put An be the sum from n1 up to capital N of Ans, and put Bn to be the sum of Bns. Then, of course, An, Bn are increasing because both An and Bn will be positive. We'll be adding positive terms all the time, so the sums will increase. Okay. And moreover, An is always less than Bn, and this happens, okay, for all n after n. Now, from this point on, for the first case, that is, Bn is a convergent series, so we assume limit of Bn exists. Okay. Well, this limit, because Bn's are increasing, will be bigger than Bn's. Okay. So Bn is less than or equal to limit Bn, since Bn increases. But therefore, An is bounded. And of course, increasing, so convergent. Well, this means that the series is convergent, and so the series from 1 to infinity is also convergent. Okay, 2 is proven similar to the case in the comparison with improper integrals. I will not go into that. 2 is similarly proven. As in the proof of the integral test. So again, to apply the comparison theorem, we need first ultimate positivity of the terms, non-negativity rather, and of course the dominance must hold. Now let us see some examples. Okay, consider the series, which is like n over, say, n cubed plus 2. Now, we are not in a position to calculate the exact value of this sum, etc., but we want to determine whether it is convergent or not. Now, we observe that these are positive terms in the first place, and certainly it is bounded by 1 over n squared term-wise, and this is true for every n. So we don't need to use the ultimate part. But also, the series is convergent since p is 2 and it's bigger than 1. By the p series, we already know this is convergent. So by comparison theorem, or the comparison test, okay, the given series, that is n over n cubed plus 2, is also convergent. Okay. As a second example, let us consider the series of sine n minus 1 divided by, say, n to the power 3/2. Now, when we look at this an here, okay, we observe that it's not positive. So we have a problem, but the problem is not a big one, namely, it's not positive, but it's always negative, because sine n cannot be bigger than 1. So it's always negative, which means that we can consider instead, okay, the negative of the series. Which is in fact 1 minus sine n over n to the 3/2, and this is always a non-negative number. Actually, it's always strictly positive. Okay. Well, we get then this inequality all the time. Now, sine n can have negative values, but nothing smaller than -1. So this is always less than 1 plus 1 over n to the 3/2. Okay. Thus, since the series 1 over n to the 3/2 is convergent, okay, so is the series 2 over n to the 3/2 is converged, because the limit will still exist. Well then, by the comparison theorem, the series 1 minus sine n over n to the 3/2 is converged. Well, that means there's a certain limit of partial sums. So if you multiply it with a minus sign, okay, you will have the negative of that limit, but still you will have a limit, and therefore, okay, the negative of this is convergent as well. Okay. So positivity here can apply to ultimately negative as well. As a third example, let us consider the sum of n over 2 to the. Well, clearly here, our an is positive for all n. We don't have a problem there. But in all such cases, okay, unlike the first example, okay, we don't have a clear-cut dominating sequence, a bigger sequence whose series is convergent. Okay. Now, when we look at the limit, we clearly see that it is 0. This is because the limit x going to infinity of x over 2 to the x is 0 by L'Hopital's rule. Okay. So, okay, we can think of this series possibly convergent. It could be divergent as well. So we consider, okay, the possibility that the series is convergent. It's just a guess at this point. Well, we have to compare it with another series whose terms form a convergence series. Well, what do we know about convergent series at this point? We have geometric series, or okay, we have the P series. So, say we try, okay, this one. Because we know if P is 2, this will give us a convergent series. And so, by comparison theorem, the wanted series will be shown to be convergent. However, the last inequality is not correct for every n. Namely, okay, this is false. Okay, actually, this is not correct for all. By trial and induction, we can show the following. We can show that n cubed over 2 to the n is less than or equal to 1 for every n after 10. Okay, as I said, it is by trial. Okay. So, this says that by comparison theorem, the series starting with 10 is convergent, because the second one is convergent. And we conclude that the series starting from 1 is also convergent. Now, here, if you look at the way of our thinking, we said that because the limit of n divided by 2 to the n is 0, okay, we thought that it could be convergent in the first place. And then, if we replace n with n cubed, the same limiting process gives us 0. So actually, to find a bound, okay, we guessed that we could use a certain limit. So, alternatively, we could have said the following. Okay. Limit n cubed over 2 to the n is 0. Okay, we can show this, okay, as before. So, there is an n0 for all n after that. Okay. N cubed over 2 to the n is less than 1. And this is what we want. So, okay, n over 2 to the n is less than 1 over n squared for all n after n0. And then we proceed, as before, we apply the comparison theorem. So what's the point? We don't have to find this n0. There is an n0 because of the limit. And so, okay, it tells us that here we need not find this n0. Okay. Still another way of comparison could be the following. N over 2 to the n would be smaller than, okay, 1 over 3 over 2 to the n. Okay. Why would this be true? Well, cross multiply. Okay. You have n times 3 over 4 to the n. Okay. By limiting process, it means that, okay, n over 4 over 3 to the n goes to 0. Okay. So, well, of course, this is not always true again. But it will be true after some n0. So, true for all n after n0, for some n0. So comparison can still be made. So there are various ways you can apply comparison theorem. But using the limit properties certainly helps. Well, we can formulate this last part, that is using limits in comparison, in a much formal way. Call it the limit comparison theorem.